Welcome to this lesson in quantitative reasoning. Today we're going to talk about Venn diagrams with 3 sets. We have been working with 2 sets, and for 2 sets we saw that we have 2 circles, and we usually draw them so they overlap in case there is an intersection. If we know they're disjoint, we don't have to, but the generic 2-set Venn diagram is a set of 2 circles that overlap. And now we're going to talk about 3 sets, and they're going to overlap in multiple places. So they're going to overlap where all 3 sets overlap and just pairs of sets overlap. So it gets a little more complicated, so you have to pay attention to details. It's not difficult, it's just details. So we're going to represent 3 sets using a Venn diagram. We'll be given a list of sets and then put them into a 3-set Venn diagram. The key to that is starting with the intersection of all 3. Then we're going to also perform operations on 3 sets. Things like find A intersect B, then in union with C. So we're going to see things like this. We're going to have to work in steps from the inside out, where you would find A intersect B, and then to put that in union with C. So there's a multiple step process there. Again, it's not difficult. It's just details and following steps. Then we're going to show that combinations of sets are equal using Venn diagrams. So we're going to shade in Venn diagrams that represent one statement and then shade in a Venn diagram that represents another statement and see if they come out with the same shading. I'm not going to dwell on that, but we are going to take a look at that. So, Venn diagrams in 3 sets. A Venn diagram represents each set under consideration by a circle. So there'll be 3 circles if there are 3 sets. The set's elements are on the inside. That's what interior means. The stuff that's in the set have to show up inside the circle for that set. The overlapping areas between circles are for the things that are in common. So if you want to put something both in A and B, you have to put it in the overlap between A and B. And in this case, if you want to put something that's in all 3, A, B, and C, you have to put it in the spot that all 3 overlap. But if an element were just in A and B, you'd want to make sure you put it in the spot where 2 but not 3 overlap. So those are the new considerations. You'll see that this will make more sense as you see an example. So the middle is the intersection of all 3 sets. So you are going to have 3 circles, and I'm just going to draw them small over here. There's your 2 circles for A and B. We're going to add this 3rd circle down here. And this area I'm shading right here, that is the intersection of all 3 sets. Whenever I draw this, just if I don't label it, you can assume the top is A and B going left to right, and then C at the bottom. A intersect B intersect C is this shaded piece. Now, students get confused because A intersect B intersect C is also part of just A intersect B. If I just asked you for the overlap of A intersect B, it would be this whole oval thing. The intersections of 2 sets in a 3-set Venn diagram still have that same oval shape. That's something you need to remember, because quite often students don't include what's in this middle piece here. Okay, so that's what a 3-set Venn diagram looks like. As I said, the intersection is a spot where all 3 overlap, which is, again, only there. So, what do we do with our 3-set Venn diagrams? How do we make them if we have lists of elements? That becomes one thing. And I actually do this again in another video with different sets. So look for that video also. So set A is 0, 3, 5, 6, 9. Set B is 1, 2, 3, 9, 15. And set C is all multiples of 3 from 1 to 15. You have to remember what the word multiple means. It means, so 3 times 1 is 3. That's the first multiple thing. They are results you get when you multiply 3 by something. So when they say multiples of 3, it means multiply 3 by it, go up by integers. So multiples of 3 from 1 to 15, 3, 6, the next one will be 9. So set C is going to be 3, 6, 9, 12, 15. So we have 3 sets. We're going to draw 3 circles. And what I have to do is I have to find how to fill in the most constrain the overlap of all three first. So I look for elements that are in all three. So I have, this is not quite what this says here, but this is in my experience the best way to do it. 0 is not in B, so I can immediately exclude that. I have a 3 in A, a 3 in B, and a 3 in C. And it's helpful to write out C. You should write out any sets that are described. Write them in roster form. So I see that I have a 3 in the intersection of all three. It's a 5 and 8, no 5 in B, so I can stop right there. I don't have to check C if it's not in B, if I'm looking for all three. 6, no 6 in B. 9, 9, 9. Okay, and if, so once I check set A, I'm done checking for the intersection of all three. So I do have a 9 also. So the intersection of A with B with C is the first thing you find. And I see that I have a 3 and a 9. And I'm going to try to color code this a bit for you. So I'm going to write this in blue. It goes right here. There's a 3 and a 9. It's hard to see the 3 because I drew this too small, but that's a 3 and a 9, okay? So I've taken care of the 3 and the 9. I can actually cross out the 3 and the 9 out of every set. It might be helpful to, don't cross it out. If you have a piece of paper with the problem written down, don't start crossing out on the original problem. Write down the sets again so you still have the original problem to look back at in case you made a mistake. So 3 and 9 were in the intersection of all three sets. Now let me change my pen to a different color. See if that works. Yeah, it does. Now I want to find the things that are just in A and B, but not in C. So really the way I would write this is A intersect B, intersect C complement. That's what that means. A in B, but not in C. In other words, I'm not going to include the 3 and the 9 again because I've already taken care of those with the intersection of all three. So I'm just looking at sets A and B here. So do I have a 0 in B? Nope. Do I have a 5 in B? Nope. Do I have a 6 in B? No. Do I have, wow. There is nothing in just A and B. So this area right here is where you would put what's in A and B only, and that is blank. So I write no numbers in this green shaded area here. There's nothing that goes in there. Okay? Now I look for, let me change color again to try to, I think it helps when you're looking at this as a student, if I do. Or maybe I'm just being silly, who knows. What about A intersect C? Now I want all the things that are in A and C, but not in B. So this means not in B. You can kind of read it. A lot of things in math are easier if you read it out loud and translate it in your head. A intersecting C, but not in B is what the B complement means. And I've already found the A intersect B intersect C, so I'm going to skip the 3 and the 9 aren't going to count, even though the 3 and the 9 are in A and in C. I've already accounted for them in the middle there. So in A, I seem to have a 0 and a 5 that are not in C. Oh, but look, I have a 6 and I have a 6. So I'm going to cross the 6 out, and I'm going to write it in the space where, so this is C down here, this is A up here, this is B. In the space where just A intersects with C. Now it can't go in the middle because that's also in B, but it can go right here. So that number 6 goes right there, and I can now cross it out of my sets because I've placed it somewhere. Then I have to find the last one. So I do A intersect B, A intersect C, and then I have to look at just B intersect C. And let me do this in another color. Oh, let me see. I'll do this in whatever that is. B intersect C intersect not A. So just in A and C. So I look at A again. Oh, wait a minute. Is that what I did? I did A and B and C. I look at B. Sorry, I'm sorry. I mean, this is correct. B intersects C. I look at B because I don't care about A if I'm looking for B intersects C. Is there a 1 in C? Now, I've already crossed out the 3 and the 9 because they're in the intersection of all three. That's why this crossing out helps. I won't accidentally write the 3 and the 9 again over here. They only need to be written. They can only be written once, not only need. So there's no 1. There's no 2 in C. there is a 15. It's a 15. B intersects C has a 15. And this space right here is B intersects C, so I write a 15 there, and I cross it out of both sets. Now what is left is the things just in A. So the things just in A be the 0. I write that over here. It's only inside circle A. It's not inside any other circle, but it now appears on my diagram. The things just in B are the 1 and the 2. 1, and you don't have to put a comma, you just write them separately. So I've taken care of the 1 and the 2. Everything in B is now crossed off. Is everything in A crossed off? Oh, I didn't write the 5 yet. 0, 5. Now I can cross that off. See, that helps me see. And the things just in C, let's look at what's left in C. It looks like there's a 12 just in C, and I confirm there were no 12s anywhere else. The things just in C go down here. Now, if I had a universal set, that was the numbers 1 through 15, I would then look to see what numbers were missing. I see I have a 1, 2, 3. I would need to write a 4 outside here if my universal set were bigger. But for these problems in your text, they tend to just tell you use the 3 sets, join the union of the 3 sets as the universal set, which means you won't have anything out here. But if I had, I'm sorry, let me do that. If I had also been told that U is 1 through 15, and remember we can write it ... That means all the way up to 15. I would have to go through and say, all right, do I have the number 1 anywhere? Yes, I do. Do I have the number 2? Do I have the number 3? Yes. Do I have the number 4? No. So then I would write the 4 outside, like in this rectangle. We talked about that earlier. Do I have the number 5? Yeah. Number 6? Yes. 7 is missing, so that would also go out here. I don't see an 8 anywhere. I have a 9. I don't have a 10. I don't have an 11. So anything that, if I were told this is the universal set, most of the problems in your book just use the union. They just use A, union B, union C, which means all the numbers listed here are your universal set. And if that's what it says, then you don't ever have anything on the outside. But if I had gone 1 through 15, I would have had a bunch of numbers on the outside, 10, 11, 12, and I would have had 13 and 14 out here also. Because everything in the universal set, if universal set is defined separately from your 3 sets, has to appear in this rectangle. Our problem just said to use the universal set as the union of the 3 sets, so you won't have anything outside of the circles in that case. That's a helpful hint. All right, let's move on. So, this is the solution they provided. They did not put anything just in C. I had something that was just in C. Or maybe they're not done yet. Oh, I had something just in C. I wonder why. The number 12 was just in C. I think they left the number 12 out of C. They forgot that. So mine is correct and theirs is not. I'm going to have to go in and change some of these slides. They were provided for me by the publisher, but they're not. Oh, was 12 in B? 12 was not in B. Yeah, they made a mistake here. Mine is correct. Theirs is not. So, suppose we have 3 sets. We're going to perform set operations on 3 sets. I'm going to stop here since this video has gone on to about 13 minutes now. I will go back in and fix those PowerPoint slides too. My video is correct though. So I'm going to stop here, and in the next video, so this is part 1 of 2, we're going to talk about performing set operations on 3 sets. All right, thank you for joining. I'll see you in class. Email me your questions.